How's it going, guys? Welcome back to another video for the AI for Aspiring Researchers lecture series. Today we're going to be going over the naive Bayes algorithm, and specifically we're going to be using the MNIST dataset. Now, if you don't already know what the MNIST dataset is, it's basically just a handwritten image classification dataset, right? So if I were to give you the handwritten digit 5, you would have to predict, or the computer would have to predict that, well, given this image, that is the number 5. And the reason this is kind of a really popular data set is, one, it's really easy to use. Two, it's kind of that very preliminary data set that a lot of beginners and actually researchers use for machine learning in general. And three, it's kind of, I guess I said this already, but it's easy to understand. And it's easy to work with, and it's easy to see exactly what is going on behind the scenes. Right, and so let's get started. Alright, so the first thing that we're going to do is go ahead and import the required libraries. Right, so the first thing that we're going to import is import NumPy as NP. Now, if you've already seen my video on linear regression with sklearn, you'll know that NumPy is basically just a library that allows machine learning researchers or machine learning practitioners to do matrix calculations much faster. And that's why you'll see in almost any machine learning algorithm or code, you'll see NumPy being used somewhere. It is extremely popular, if not the most popular library in the machine learning world. Alright, so the next thing that we're going to do is import matplotlib, oops, I cannot spell, matplotlib as PLT. Right, so matplotlib.pyplot as PLT, what this is doing is it's basically giving us a way to graphically represent the data. And you'll see that in the future of our code right here, we're going to be graphically representing how accurate our naive Bayes algorithm really was using a heat map. And I'll explain that in the future. Okay, so the next thing that we're going to do is from sklearn.naive_Bayes import Gaussian NB. Now, what Gaussian NB stands for is just Gaussian naive Bayes. It's another type of naive Bayes that essentially predicts using a Gaussian distribution. And if you want to learn more about these different kind of naive Bayes tactics, I'll put a link in the description that gives the different libraries for I think there's Gaussian naive Bayes, multinomial naive Bayes. I think those are probably the main two that are used. And then, yeah, so you can go check those out. Alright, so the next thing that we're going to do is from sklearn metrics import confusion matrix. Right, so what a confusion matrix, if you don't already know what that is basically there is going to be a predicted value and an actual value, and I think actually I'll explain this later because I feel like it'll make more sense when you visually see it. Alright, and the final thing that we're going to do is from TensorFlow.keras.datasets import MNIST. Now, you might already guessed, this is basically where we get our MNIST dataset. And if you don't know what TensorFlow is basically a package developed by Google that has a lot of machine learning things. So in the future, we'll be going over, say, neural networks. And TensorFlow allows us to create these neural networks much faster and the coding is much simpler, and it's just a lot better for us as a programmer to use TensorFlow, and so I would personally recommend it. Alright, so now that we have all our libraries and packages installed or imported, we need to load the data set. Right, so what we're going to do is with the MNIST dataset, it comes with an X train, a Y train, and an X test, and a Y test. Right, so these are basically, the X train is just the values of the image that we're going to see, and I'll show you exactly what those values are. So this is the values of the image, and then what the image is actually showing, meaning what number it is, right? And then same thing here with X test and Y test. Alright, so we're going to say that is equal to MNIST.load data. And load data just means it's going to retrieve that data from whatever package. Okay, so now we're going to say X train is equal to xtrain dot reshape 60,784. And then similarly with xtest is equal to xtest dot reshape and 10,000, oops, not 100,000, 10,784. Right, so what this is doing is it's basically saying, okay, we have this xtrain data, but we need to make it in such a way that we can use it. Now in the xtrain data, there are 60,000 examples, and same with xtest, but in xtest there are 10,000 examples. And you see the 784 number. Now the 784 number is not arbitrary, right? So in every single image of the MNIST dataset, it is going to be a 28 by 28 size, and 28 squared is basically 784. So 784 is basically the number of pixels per image, right? So you have 60,000 images with 784 pixels each for the xtrain, and similarly for xtest, you have 10,000 images, each with 784 pixels. And so that's why we want to reshape with these parameters. And reshaping just basically, once again, it allows us to kind of mess with the data or kind of change the data in a way that we can use it more effectively. Right, okay, so now let's run that. It's downloading the data. And let's just see exactly what our X test would look like. Right, so X test. Right, so basically what this is doing now is you just see a bunch of zeros, but you see them in a 2D matrix. Right, so what this is doing is that this row right here represents the first image. This one represents the second image, and all the way down to the 10,000 image. Now the reason you see zeros here is because these are just representing colors. So the color of the pixel, right? And so I think it would be better if I instead showed you the actual image or what's actually going on behind each pixel, or sorry, each row. Right, so now let's just see that. So plt.imshow x underscore train and 0. So what this is doing is getting the first image in the training data set. Sorry, dot reshape. Now 28 by 28. So this is just kind of putting it back in that 28 by 28 pixel format. CMAP is equal to gray. And so this is just a grayscale image. And plt.show. And once again, this is how we use our plot or matplotlib. We're able to visualize the data. Right, so here we go. Right, so now we see the number 5 here. Right, so this is essentially what the very first image is. So if I go back here and instead say xtrain, you'll see same thing. But in this case, this first row is essentially representing of the 5. And now there's obviously these ellipses in between, and you'll get different numbers in between there. So let's see actually one thing. If I try doing this, what will I get? Right, so what you can see is this huge array, right? So this is going to be essentially 784 pixels, and each of these numbers you see here, these are all going to represent different colors that in the end come out to be this 5. Now if I say did a 1, you'll see a different number, right? So this is the number 0. So this is the first element, or I guess the 5 was the 0th element, this is the first element. If I try 2, you'll see the number 4. And then so on. You can kind of just play around with this to see exactly like what different types of, how the different types of digits look like. But essentially you're going to get the digits 0 to 9 all kind of represented throughout. Alright, so now that we have our, sorry, one second. Now that we have our data loaded, what we need to do is actually build the naive Bayes kind of model. And so what we're going to say is naive Bayes model, or NB model, is going to equal to Gaussian, and Gaussian, oops, can I spell today? Gaussian NB. Right. And so what this is doing is it's essentially creating that Gaussian naive Bayes model through using this package right here. And it's doing it all for us. And so that's why it's going to be of nice use to us. Alright, so NB model is equal to Gaussian NB. Now the next thing that we need to do is we need to actually fit our data for this model. We need to fit the model on the training data. And so what we're going to say is fit NB is equal to nb underscore model dot fit, and then we're going to say x train, y train. And so what this is doing is it's basically taking this X training data, or these images in our training data set, and the corresponding Y values for them, meaning if this is the image 4, the corresponding Y value would be a 4. And then it's going to fit our naive Bayes model on this data, and it's going to kind of send it back and store it in this fit NB variable right here. So let's run that. Awesome. And so the next thing that we're going to do is say predictions is equal to fit nb dot predict, and then we're going to say x train. And then basically what that's going to do is it's going, or sorry, not x train, it should be x test. Right, so now what this is going to do is basically in this right here, we're fitting it on the x training data set, and so we're kind of fitting this model, we're making it better. And now over here, we need to actually predict how well it did. And for that, we're going to be using our x-test data set, right? So now we're going to say con matrix, or confusion matrix, or sorry, no, con matrix, we're just going to call it that for now. Con matrix is equal to confusion matrix, matrix there. I was waiting for it to finish for me. Alright, y test predictions. Alright, so now what this is doing, and I said that I would be talking about what a confusion matrix exactly is. What this is doing is it's basically just essentially going to show us that on the x-axis is basically the predicted values, if I'm not, yeah, right. So the x-axis you can kind of think as the predicted values, the y-axis is going to be the actual values, and you're going to see exactly what happens. Oh, predictions is not defined. Oh, whoops. Let's change that then. Right. And so what we get here is this whole matrix right here. And you can kind of see right off the bat, there's a lot of numbers on the diagonal that are much larger than all the other numbers over here. So you see like 1, 2, 5, but then over here on the diagonal, you see like 870, 1079, 266, 353, and kind of a lot of numbers over here as well. Well, what this is essentially saying is that, okay, this right here is the actual value is going to be a 0, and I predicted 0. So for 870 images that were actually 0, my algorithm, or the Gaussian naive Bayes, also predicted 0, right? But and same thing with over here, right? So for 1079 images that were actually the number 1, or the digit 1, I also predicted 1. And then same thing all the way over here. So for 955, there were 955 images of the digit 9 that were actually 9 that I also predicted 9. But you can also see these numbers that aren't on the diagonal. So what those mean is, let's take this one, the 79, right? So for 79 images that were actually the number 2, because this is in the kind of tooth index, for 79 images that were actually the number 2, our Gaussian naive Bayes algorithm actually predicted them to be 0. And you can kind of think of that for any of these, right? So for this one, let's say, for this one, there are 10 images that were actually the number 7 that were predicted as the number 3. And you can kind of see some zeros in here as well. So what that means is that there were no images that were some said number that were also predicted incorrectly, right? So the diagonal, you can kind of think, are the correct predictions, right? These are the correct predictions that we're predicting exactly what the image was showing and exactly what was shown in the Y test. Whereas anything that's not on the diagonal is not like that, right? So that's going to be the incorrect predictions. And so you can also notice one thing, you have a lot of large numbers kind of all the way swayed to the right. What that means is that we're predicting, or the Gaussian naive Bayes algorithm is predicting it to be the image to be 8 and 9 several times for many different digits. And that's kind of a word of caution for naive Bayes, because like the name itself says, it is naive. It's really rudimentary in the way that it works. And you'll see in future lecture videos how we can improve on this using more advanced techniques such as, say, neural networking. And so that will be a lot more beneficial to us as well. But for now, I think this is performing fairly well, right? So we're able to see kind of this strong diagonal presence right here. All right, so one more thing, or I want to also kind of write a method real quickly to kind of see what exactly the accuracy on this thing was, right? So we're going to say definition or def diagonal sum, and then it's going to take in a confusion matrix or a con matrix, and in here we're going to say sum is equal to 0. Oops. Sum is equal to 0. So what this method is essentially doing is I just want to sum the diagonal to see how many images were actually corrected or correctly predicted, right? So we're going to say sum is equal to 0 for I in range 10. Now this is just going to iterate through all the digits, and we're just going to have to do a double or a nested for loop. So for j in range 10, and we're going to say if I is equal to j, if I is equal to j, sum plus equals, confusion, or the con matrix, I, j. Right, so now what this is going to do is it's just going to take whenever the indices of, or whenever the values of I and j are equal, so if this is 0, 0, it's going to take 870 and then add it to sum, and it's going to do that for all of these and keep adding them to sum until we are kind of through with all of the values, right? And then we're just going to return sum. Okay. All right, so now what we are going to do with that is we're going to say sum is equal to diagonal sum, and then we're going to throw in our confusion matrix, right? So con matrix, right? And then what we're going to say is print sum. So what this is just doing is it's kind of sending or kind of applying this method, and we just want to essentially add up all the values on this diagonal. So we're going to print sum. But one more thing, I also want to see the accuracy of this. So we're going to print, and then here, accuracy, and in terms of, say, percentage, right? So that, oh, whoops. And then we're going to say sum divided by 10,000. Okay, so first of all, what I'm doing here is I'm using an f string, and that's what this means. And this is like a really nice way of doing it, because all you'd have to do if, say, you want to implement or add a variable into your string is use these curly braces. And then inside the curly braces, I say sum divided by 10,000. Well, the reason I'm using 10,000 is because we had 10,000 values in our testing data set. Remember right here how we reshaped it to 10,000? Right, so we're using 10,000 values in our training or testing data set. And so for that, I want to say the sum, which is essentially these number of values added up together, divided by 10,000. So the total number of correctly identified digits divided by 10,000, and that will give us our accuracy. Right, so here we have an accuracy of essentially 55.58%, which isn't that good, but once again, remember that we're using the naive Bayes algorithm, which once again, in the name itself, is naive. So we're not going to be achieving like 95% accuracy on, especially a fairly complex or fairly complicated data set as the MNIST, because it has several different values, as you can see in this matrix right there. All right. I want to do another thing just for curiosity. Basically here we tested it on the X test, but maybe we can also test it on the X train and see how well it performs there. So what we're going to say is predictions 2, it's just another predictions essentially. So fit, and then fit nb dot predict X train. Right, and then we're going to just say con matrix 2 is equal to confusion underscore matrix, and then y train y train, and then we're going to send in this time predictions 2. Predictions 2. Right, so essentially what we're doing is we're taking this x train, we're fitting it on the naive Bayes class, and then we're going to take predictions, save that as predictions 2. Then we're going to make our second confusion matrix using the y train values and our predictions 2. And then now we're just going to print con matrix and then 2. Right, so let's see what it does. And so this is going to take a little bit more time, and the reason is because in the first one we're using only 10,000, but here we're trying to predict for 60,000. Right, and so you see these numbers, right? So once again, you get you get much larger numbers on the diagonal, and kind of a lot of numbers over here as well. So we're going to do the same thing, and once again, I am very lazy. So what we're going to do is we're just going to copy paste this and change some variable names right there. Right, so sum2. We're just going to call it sum2, and then we're going to use our con matrix 2, print sum2, accuracy sum2, and instead of 10,000, we're going to be using 60,000, right? Okay, let's see that. And so you only see an accuracy of around 56.49%, which is actually very similar to the testing dataset. And the reason it's so low is, once again, naive, right? It is the naive Bayes algorithm. It's not neural networks or anything, so the accuracy is going to be significantly lower than, say, if we were to use neural networks. All right. Now, I also want to kind of visually see these confusion matrices, because it's good to see it like numbers, but honestly, everyone would like to see them like with colors. So what we're going to do is we're going to say a plt.imshow, and then we're going to send in our confusion matrix, the first one. So this is with when we're predicting the testing data set, and then we're going to say cmap is equal to inferno, and I'll explain what that means in just 1 second. Interpolation is equal to nearest. Okay. Well, let me actually just finish this piece of code. So plt.x label, and we're just going to call that our predictions, and then plt.y label, y label, and we're just going to call this the actual values for the MNIST, and then plt.show. Okay, so essentially what this is doing is this first line right here, plt.imshow, the confusion matrix, this con matrix, is just essentially this matrix that we're using for x-test. cmap is equal to inferno is just a color theme. There are, I believe, many different color themes that you can go through, test yourself. I just personally think inferno looks pretty cool, so I'm using that. And in interpolation equals nearest, you just kind of want to use that. Okay, plt.x label predictions, and plt.y label actual values. That's just axes values, and plt.show. So we're going to run this, and we get this confusion, or we get this heat map essentially, right? And so on the diagonal, you can clearly see that it's much brighter colors, right? And so what the brighter colors mean is that the values on that diagonal are much higher. And you can also see kind of brighter colors swaying off to the right as well. But for now, we're going to focus on this diagonal right here. And that's what essentially representing this diagonal over here. These much larger numbers have much lighter colors, right? And so what we're going to do is now we're also going to do this for the second confusion matrix, right? So we're just going to say con matrix underscore 2, and then same thing. So yeah, so right, we get a very similar map, and the reason for that is because the percentages at which they're essentially predicting these values are going to be very similar. So this is 5206 divided by 60,000 is actually very similar to like 870 divided by 60,000. I'm not sure exactly how similar they are, but actually we can check that out. So print, I'm not sure if this works. I've never actually done this before, but print 5206 divided by 60,000. I don't know why. Right, and so we have print, you can also do print, and then 870 divided by 10,000. Right, and so you get very similar numbers, right? And so what these similar numbers mean is that the shading or the color on this heat map is also going to be very similar. You can see some slight differences, but for the most part, these two maps are very similar. But the point of these two maps is basically to show you that the lighter the colors on these heat maps, the more the value is, whereas the darker the colors, the less the value is, right? And so that's the main purpose of the heat map, and that was essentially the naive Bayes algorithm and how it's used. Um, I would say that the naive Bayes algorithm can also be used on any essentially classification problem. If you feed in a kind of set of data or set of kind of variables or features and expect some sort of classified out or classification output, naive Bayes would be a good start for kind of seeing how well or kind of testing the data set. And so in this case, there's no explicit features per se. That's not like the iris data set where you have like the lengths of petals or I think like sepal lengths or petal lengths. But here we kind of used or kind of created our own features, and we said that each single pixel in this image was another feature, right? And so each single pixel was a feature even though it wasn't explicitly defined as such, right? And so that's what you see in this matrix right here. These all these values, right? All these values right here, these are all features that we're using for our naive Bayes algorithm. Now, once again, I just want to I know I've mentioned it several times, but it requires me to mention it another time. Naive Bayes is naive. It is very elementary in terms of the way it works, and we'll look in a future video or for this lecture series, we'll apply neural networks to MNIST dataset, and you'll see that the accuracy of neural networks is so much better, so much more significant than the naive Bayes or even Gaussian naive Bayes algorithm, and you'll see that in a future video. Once again, kind of ending this off, if you like what you see here, feel free to subscribe, like, share, leave a comment, kind of telling me what videos you want to see next. If you had any questions, I'll be more than happy to answer them. And until next time, see you guys.